Well, hello there. You may recall that in a previous video we took a brief look at this amazing breakthrough in locomotive technology. Now, never mind mysteries like dark matter, gravitational waves, grand unified theories, and the expansion of the universe. If YouTube is any indication, this janitor and his mop bucket is really the hot topic in physics right now. Now, we've already seen that if you look carefully at the video, you can see he's riding on an electric skateboard. So that particular example is fake, but here's another popular YouTube channel called The Action Lab, where this guy takes up this recent video that we just looked at.
Hey everyone, today we're going to be seeing if you can blow your own sail. So recently somebody sent me a video of a janitor riding a skateboard, holding up a sail and then blowing it with a leaf blower, and it made him go forward. So let's go ahead and evaluate this and see if that would actually be possible. Something seems a little off here. I have here a mini version of that little setup. It's a car with wheels on it with a strong fan. So first let's put a board in front of it, this polycarbonate sheet here. And let's see if this is actually able to push itself on the ground. Okay, 3, 2, 1. Doesn't go anywhere. But now take the board off. It's not going anywhere. But remove it. It actually goes really fast. So you can see that in order for this to even go, I had to take off the board that it was blowing on. Without it, it was able to fly freely. Okay, so first we're gonna be trying it out just like I saw in the video. The sail in front of me, and I'm gonna be shooting it with the leaf blower here. So let's see if it actually works. Okay, 3, 2, 1. Doesn't work. Not going anywhere. To do to get this to work, take off the sail, turn the other direction, and there we go. Woo! But why is it that when there's this board in front of it, it won't go? There's air pushing on it, so why doesn't it push it forward like that? Well, let's look at the forces involved here. Okay, so right now this weighs 0 grams. Okay, and then turn on the fan. It weighs 22 grams. So you can see that when I turn on the fan, it's the equivalent of putting 22 grams, or turn it to force, 0.05 pounds force in this direction. Now the only reason that works is because it's throwing air in this direction, and due to the propulsion of mass in this direction, it gets pushed the opposite direction.
That's, of course, Newton's third law, equal and opposite force pairs.
But now what happens when we put this in front of it? Now turn on the fan.
Now take note of that number. It's close to 0, but it's not 0. There does appear to be a net force, which the host here basically disregards.
So you can see that when we put this on it, it basically weighed about the same on the scale. There was no real significant force on it. And we know there's no real significant force because it doesn't go anywhere. It can't even overcome the friction of the wheels to move.
So I suppose he is acknowledging that there's some force, it's just not enough to overcome friction.
So why doesn't it move? It's because the fan is still throwing air in this direction, but then when it hits the sheet right here, it creates a force in the opposite direction. So this fan is throwing the equivalent of 22 grams of air that direction, which makes it want to go this direction, but then those 22 grams of air hit this and make it want to go that direction.
Now he's talking about the mass of air thrown forward. The relevant quantity here would really be force. In the act of accelerating that air forward, a certain force must be applied, and the scale that he's using doesn't give force in newtons, it gives the equivalent mass. So we really shouldn't be talking about how many grams of air are pushed forward, but rather the force required to accelerate that air.
Direction, so they exactly balance each other out and it doesn't go any direction. So of course, if you want to move somewhere, if you want to be moved somewhere with air, you can't let it hit a plate in front of you. You have to let it blow off in the other direction, and then you can go this direction. I look like a fool because everyone's like, that doesn't work. Either the leaf blower or just the sail, but not both of them together. So let's try just the sail. Come on, wind. Now, if only I could steer it.
So the Action Lab is a great physics channel. There's some really enjoyable content on there that's related to our curriculum and the curriculum that you'll see in subsequent classes. But on this particular issue, the host seems to have come up short because remember, our old pal Bruce Yeany took this a little bit further and actually constructed a little sailboat that can push itself forward with a fan.
I think we're ready to give this a try here. Face it. And off it goes. Yeah, it works pretty well. I really am surprised at how well this works. So Dr. Doolittle and Wile E. Coyote actually would have been able to move themselves by blowing into their own sails.
And let's also not forget that Mythbusters, as early as 2011, possibly before, I say 2011 because that's when this video was uploaded to YouTube, Mythbusters had already demonstrated that you can, in fact, blow your own sail.
All right, you ready to do this?
Ready.
Okay, here we go. This is blow your own sail with the full-size boat.
I gotta tell you, the funniest part about this whole experiment is when we first turned on that fan and the boat just started to spin and dip down in one direction. Grant and I both were super wide-eyed because we thought we were going over.
They're wildly out of control. There's no forward movement, just a whole lot of spinning and crashing.
So when we first started and I gunned it, we started turning in a circle and I was like, this is it. That's it. We're going in the water. But I turned it down and we tried it again, and actually what I found was, it's moving forward. You keep vectoring the fan. If you keep that thrust at the sail, you can actually get it to go forward.
There she goes! Look at it! They're going forward! We blew our own sail! It's working!
By style, the team has seemingly contradicted Newtonian physics. It's working. They're blowing their own sail.
Violation of Newton's laws. Is it necessary to jump to that conclusion? That seems a little hysterical. So let's see if we can make this plausible. And in the following slides, let's imagine a very simple boat with a rectangular sail like the ones you see here. And if you do a Google search, you can find a whole bunch of images of the possibility of blowing your own sail. I guess this is something people have thought about for a long time. You've probably seen it in cartoons. Here's my little cartoon picture of our boat from the side. Let me grab my laser pointer. So the sail is mounted on a mast, and here's the fan. Now, I'll be honest, when I look at that fan, I'm not entirely convinced that I've got it facing the right way. Like suppose it were to, if you're looking at it from this direction and you get it rotating clockwise, I don't actually know if that would blow air to the right or to the left. We'll take that problem up in a later video when we look at turbines after we've talked about torque and angular momentum. And of course, we need some sort of power supply to keep that fan turning against air drag. And now let's just boil this down to the essential mechanics, if that's even possible. Forget about the fact that even a handful of air has something like a trillion air particles in it. Let's just look at the interaction between a single air particle and the fan. Or you could say the interaction between a single particle and the boat, since the fan is attached to the boat. Let's suppose that in the act of turning, this fan launches that air particle forward. And we know from Newton's third law that there will be a reaction force backwards. And now that we've talked about momentum, let me back up. When these two are just sitting here, the particle of air and the boat, there is zero momentum. If you want, you can call this the x direction, but we're only interested in motion along that axis, so I'm not going to worry about subscripts here. During this isolated interaction between the fan and the air particle, momentum should be conserved. So after they start moving, there should still be zero momentum. So if the air particle gets launched forward, the fan and hence the boat would have to be launched backwards. So I will use these symbols to refer not to the actual velocities, but the magnitudes of the velocities. In other words, the speeds. So VA is a positive number. It's how fast the air particle is moving, and VB is how fast the boat is moving. And I tried to string some slides together, and I'm just going to hold down the button, and let's see if this actually animates correctly. Oh yeah, so let me back up, do that again. Rewind. You'll notice when the air particle reaches the sail, it's going to bounce off the sail, go backwards. And I'm making the assumption that this is an elastic collision, meaning one in which kinetic energy is conserved. This is an elastic collision in which the boat and the air particle merely reverse their directions but maintain their speeds. So if both speeds are the same before and after, there's no loss of kinetic energy. So observe how the arrows switch direction when the air particle bounces off the sail. All right. And you see that the net effect, despite the fact that the air is initially launched forward and the boat is launched backwards, the net effect when that collision is done taking place is that the boat is pushed forward and the air is pushed backwards. So that wasn't totally intuitive to me, but when you see this animation, hopefully that makes it much easier to conceptualize. Let's look at that one more time. This is in reverse. Okay, so when the fan first kicks the air forward, the boat gets a little push backwards, but then there's that collision between the air and the sail, and that leaves the boat going forward. Now, I just imagined that the air particle kind of passed through the fan blades or maybe around the fan blades. Let's not worry about that. But if there were no other forces in the universe, if this was happening out in space with no gravity, air drag, friction whatsoever, then you would imagine that the boat would now continue forward. So you can push yourself forward by pushing air forward. You have to have some kind of barrier in the front that reflects the air backwards then. And so you may be wondering, well, if this is working in this little animation here, how come it didn't work in the Action Lab video? Before we let Bruce Yeany take up the answer to that question, let's just make sure that this is mechanically plausible. Are we violating any basic laws of physics here with this animation? Let's check that we can conserve momentum and mechanical energy in this process. So in the upper right here, capital P is for the total momentum. Remember, I'm using the symbols VA and VB as the speeds, so it's up to me to assign minus signs when I know that a momentum is negative. So here's the positive forward momentum of the air particle after being launched by the fan, and here's the backwards negative momentum of the boat, which is kicked, it recoils in the opposite direction. That's my initial momentum. And after the collision, whoops, let me back up. After the collision, we've got final momentum, which can be calculated as follows. Remember now the velocities have switched directions but maintain their magnitudes. So now it's the air particle going backwards with that negative momentum, same speed that it had in the forward direction, and the boat now has the positive momentum. So this is the final momentum of the system. This is the initial momentum of the system. And in order to conserve momentum, those two quantities would have to be equal. So I've just set this quantity equal to this quantity. And what does this equation tell us? Well, let's check this out. MAVA with the minus sign. Why don't we scoot this to the other side? And then MBVB with the minus sign. We'll scoot this over here. We get this equation. Of course, the 2's cancel. If you solve for VA, evidently, the only requirement in order to conserve momentum is that the air particle must be moving considerably faster than the boat. See, if you take the boat's mass compared to the air particle's mass, you get a huge number. Now, again, this whole device is a little silly because how can you possibly have an experiment where a boat is pushing on a single particle of air? Because when you get right down to it, air particles don't even really behave like little balls of mass. When you get to the atomic scale or the molecular scale, things behave more like waves. So you can't really do this in actuality. But when viewed from the perspective of 19th century mechanics, or before, just basic mechanics, we can at least show that there's no violation of fundamental physics here. If we also need to conserve kinetic energy, because remember, I just made the assumption that this was an elastic collision where the final speeds were unchanged, then we get this equation. I'll draw your attention to the fact that initially the air particle is moving to the right, then it was moving to the left. But of course, when you square this term, the minus signs go away. And that means this quantity is actually the same as this quantity, right? The kinetic energy of the air particle before and after the collision is the same. So you can just subtract those quantities from both sides and you end up with 0 equals 0. So that's trivial. You can trivially satisfy the constancy of the kinetic energy just by letting the particles, or the particle in the boat, have the same speed before and after. Okay, so hopefully I've demonstrated that it's plausible that this could happen. Neither of these principles are being violated. And I really shouldn't call this a principle because the conservation of kinetic energy is not necessary. In fact, most of the time that's not the case. Most collisions are not elastic. Now, earlier in this video, Bruce Yeany had already spoken about the fact that the only way he could get the boat to blow on its own sail and actually push itself forward is to have a curved sail. The sail had to have the right shape and curvature. He tried it at the beginning of the video with a flat board, maybe a piece of plastic, just like you saw in the Action Lab video, to no avail. The only way to redirect the air and have it go backwards is to curve the sail. So that's a little more complicated, or probably a lot more complicated than what I showed in that silly animation, where I'm just assuming, you may have noticed I made the ball even, or the particle of air squish a little bit, almost like a rubber ball, as it bounced off the sail. Well, the interaction between air molecules, especially en masse, and a sail is more complicated than that. But he's got a little graphic here that helps you understand that the overall effect is similar.
All right, now that mess is cleaned up, let's see if we can make another one. Sorry, this is part of my safety equipment for this next part, along with a very strong exhaust vent right above me. What I want to do is produce a little bit of smoke or drop some powder into the moving air to see what kind of airflow we get as the air strikes the surface of this sail. So let's see what happens.
In this first attempt, we can simply see the smoke being drawn through the fan as it pushes air forward. Now let's put the flat sail on. With the flat sail in place, we can see that the air is simply diverted off to the sides. Now here's where the airflow really gets complicated.
Now this is just the fan cart's fan blowing into its own sail. Now the air movement starts when the fan is turned on and it pushes air forward. The reduced pressure behind the fan in turn draws more air into it. The next step is when the air hits that sail, it's redirected backwards. But not all of it continues backwards. Some of it's redirected back into the fan a second time. It looks like we have even additional air movement towards the sail without going directly through the fan.
Okay, so the details of the motion are obviously quite a bit more complicated than a simple one-dimensional elastic collision between a particle and the sail, but the overall transfer of momentum is basically the same. Now, I don't know that the air particles are coming in at the same speed at which they go out, but supposing they are, the before and after is really the same as what we were looking at. Now, you may be wondering at this point, what is the purpose of installing the sail and going through the trouble of redirecting the air if you could just, if the net effect is to send air backwards overall and send the boat forward, then why not just turn the fan around, get rid of the sail? I haven't gotten rid of the sail in the picture here, but just pretend it's not there, and just launch air backwards, which would send the boat forward. After all, that's what you saw the guy in the Action Lab video do. And that might look something like this. Oh, I'm getting ahead of myself there. So let's look at that a little slower. The fan imparts negative momentum. You know, if we're calling to the right positive, the fan imparts negative momentum to the air particle, and so the boat would have to acquire positive momentum. Right? It's the same net effect that we saw earlier. And this may not be any surprise to you because of course, this sort of thing happens all the time. It looks like it's popular down in the Everglades where they use what are called airboats, not fan boats, but airboats. In fact, I remember one of these featured in that movie Waterboy. I tried to find that scene on YouTube, couldn't find it. You can, however, find plenty of other footage on YouTube showing airboats in action.
For over 85 years, airboaters have used this 110,000-acre parcel of Everglades as their playground. But in 1989, it was added to the Everglades National Park, where airboating has been off limits. For the last 26 years, airboaters have been fighting with the National Park Service. They want to pass along their hobby to their children and grandchildren. But Congress says when they die, recreational airboating does too.
I've grown up on airboats.
21-year-old Taylor Rhodes is among those who will be banned.
It's like a dying breed. My grandpa's took me out here from when I was a kid. I got pictures of that boat ramp when I was 5 years old.
Didn't they make a movie about this? I seem to remember a movie called The Last Airboater. Okay, I just looked that up and I was mistaken. It was The Last Airbender. Oops. So the last thing I'd like to do here is attempt to make this plausible even with a myriad of particles, a multitude, a plethora of particles instead of just a single particle interacting with the fan. So here's the best I could do. Oops. Let's try that again. I'll go slower. You can see air going forward, striking the sail, recoiling at the same speed, and all the while the boat is still moving forward. And the net effect is to throw air backwards and throw the boat forward. Okay, case closed, I hope.